All right, let's just dive right in. We use words like most, few, and many all the time, right? Dozens of times a day without even thinking about it. But have you ever really stopped and wondered what they actually mean from a logical point of view? Turns out the answer is way more fascinating than you'd probably guess.
I mean, just take a simple word like most. It feels so natural, so intuitive. But if you had to define it using pure cold logic, how would you even start? For a really long time, this was a massive puzzle for logicians and linguists. Why? Because their traditional tools just weren't cut out for the job.
And that's our starting point. You see, to really appreciate the breakthrough here, we first have to understand the problem they were up against. The world of classical logic was, well, a little bit limited. And this slide really lays it bare. For centuries, formal logic pretty much had only two main ways to talk about quantity: all and some. That's it. But then look at our everyday language. We've got most, few, many, at least three, exactly five. The list goes on and on. This huge gap between formal systems and how we actually talk was a serious challenge. And look, this wasn't just some minor academic issue. This limitation was a fundamental roadblock. It meant that a huge chunk of what makes human language so rich and expressive was just completely outside the reach of formal analysis. I mean, how can you claim to understand language if you can't even get a handle on its most common words? So how did they get past that roadblock? Well, it took a totally brilliant shift in perspective. And that brings us to the core idea. What if we stop thinking about these words as just symbols and start thinking about them as relationships between sets? And this is the big idea. It's called Generalized Quantifier Theory. Instead of trying to define a word like most in a vacuum, the theory completely reframes the question. It says most isn't a thing, it's an action. It's a way of describing a relationship between two groups of things. It's a huge shift from thinking about symbols to thinking about relationships. Of course, an idea this big doesn't just appear out of thin air. It was built piece by piece over decades by some really brilliant people. Mostavsky and Lindstrom laid down the core mathematical foundations, but the real game changer was in 1981 when Barwise and Cooper connected it all directly to natural language. And that's when everything just exploded. Okay, so theory is great, but how does this actually work in practice? Let's take a super simple sentence and see what's going on under the hood. Most students came to the party. Seems simple enough, right? But there's a really cool logic at play here. Here's the breakdown. First, we have two groups, two sets. Set A is simple. It's the group of all students. Set B is also simple. It's the group of all people who came to the party. Now here's the key. The word most doesn't describe set A or set B alone. It describes the relationship between them. Specifically, most is a rule about the size of their overlap, that group of students who were also partygoers. Now, here's what makes this whole theory so incredibly elegant and powerful. It turns out that these quantifiers, they follow certain rules. And there's one golden rule that seems to apply to almost every single quantifier in every human language. It's got a kind of fancy name, conservativity, but don't worry, the idea behind it is actually pretty straightforward. The easiest way to think about it is that a quantifier, like most or every, is only interested in the first group it's talking about. It basically restricts its focus. It only cares about its own little neighborhood. Let me show you what I mean. Think about this sentence. Most students are happy. Now think about this one. Most students are students who are happy. They mean the exact same thing, right? Adding that extra students who are is totally redundant. And that's because the word most has already focused all of our attention only on the world of students. To figure out if the statement is true, we never ever have to think about anyone who isn't a student. And this is a huge deal. It's not just some clever observation. It's considered a fundamental and widely accepted constraint for these kinds of words. This rule isn't just explaining how language works, it gives us a powerful test for what can, and maybe more importantly, what cannot be a quantifier in the first place. Okay, so we've got the theory, and we've got its golden rule. Now for the payoff. Let's see how this powerful new toolkit can finally handle that whole messy variety of words we saw at the beginning. All of a sudden, all of these words just click into place. Most, few, many, and even really specific ones like at least three or more than half. They can all be defined and analyzed inside this one single unified system. So let's go back to our old friend most. We can finally pin it down. Formally, it often means more than half.
In the language of sets, that means the size of the group in both A and B is greater than the size of the group that's in A but not in B. See? It's just a clean, precise mathematical comparison.
And what about something simple like at least 3? Peh, easy. The theory handles this beautifully. It's just a simple rule that says the size of that overlap between our two sets has to be greater than or equal to 3. Simple, clean, perfectly logical. Okay, I know what you might be thinking. What about the really tricky, vague ones, like many or a few? Does the whole theory fall apart? Not at all. And that's one of its biggest strengths. It can model these words too, by acknowledging that their meaning isn't some fixed number. Instead, it's super dependent on context, and the theory gives us a framework to analyze that context too.
All right, so this is all super cool if you're a linguist, but why should the rest of us care? What's the real-world impact of figured out the logic of a word like most? Here's the bottom line. Generalized quantifier theory was way more than just an academic puzzle. It fundamentally changed how scientists saw the logic that's deeply embedded inside our own language. It gave us a mathematical lens to understand something profoundly human. And that brings us right into the world we live in today. This kind of work is absolutely essential for artificial intelligence and natural language processing. I mean, if you want to teach a computer to truly understand what a sentence like, "most customers liked the new feature" means, you need a formal, logical system to do it. This theory is exactly that system. Which kind of leaves us with one last big thought to chew on. We've managed to crack the code on a huge piece of how we talk about the world. It's a massive step in translating intuitive human meaning into formal logic. So it makes you wonder, if we can teach a machine the logic of most, what subtle, complex part of being human will we formalize and teach it next? Thanks for tuning in.